Good morning. Thank you for the introduction. And I would like to start thanking the organizers of the conference for giving me the opportunity to share with you some of our recent advances in the study of molecular enhancement factors of the electronic electric dipole moment in these three diatomic ytterbium-containing molecules. So to give some context to this talk, as it has been said before, let me start saying that we know that the standard model of particle physics describes quite well matter, radiation, and interaction between matter and radiation in terms of elementary particles. We also know that using this powerful theoretical framework, we can provide quite successful and accurate experimental predictions, and also we can explain most of the laboratory experiments. However, there are some open questions that this model cannot explain. As it has been said before, the balance between the matter and antimatter in the universe, the neutrino oscillations, and the standard model cannot also explain the nature of dark matter and dark energy. And all this implies in a way that there should be new physics or physics beyond the standard model. In particular, regarding the imbalance between matter and antimatter, or the predominance of matter over antimatter in the universe, we should say that in 1967, Andrei Sakharov showed that the theory explaining this asymmetry should satisfy three conditions, and one of them is the simultaneous violation of charge conjugation and parity symmetries. And this opens the door to look or to search for physics beyond the standard model using atoms or molecules. So it is possible for us to search for physics beyond the standard model, not only using high energy physics, but also using low energy precision experiments, for example, by searching for the electric dipole moment of the electron using molecules. And this is a project that is, for example, carried on currently in the University of Groningen. So what is the theory behind this kind of searches? In 1958, Salpeter proposed this interaction, this Hamiltonian, that accounts for the interaction between the eEDM, the electronic electric dipole moment, and electromagnetic fields. Basically, it has been shown that the electric interaction dominate over the magnetic interaction. So here we only keep the electric interactions. Here E is the electric field at the position of one of the electrons, and beta and sigma are the 4x4 Dirac matrices in the standard representation. The E is the eEDM, is the magnitude of the eEDM. So schematically, we can see that if we apply parity operation in this interaction, the direction of the electric field is reversed, and the direction of the spin of the electron is the same. So the parity operator, and the eEDM Hamiltonian anti-commute, which means that, of course, the eEDM Hamiltonian is a parity antisymmetric operator. And we can do something similar with the time symmetric operation. In this case, the E field, the electric field, the direction of the electric field is the same, but the direction of the spin changes. And again, the time reversal operator and the eEDM Hamiltonian anti-commute with each other, which means that the eEDM Hamiltonian is also antisymmetric. So if we assume the validity of the CPT theorem, so the simultaneous conservation of charge conjugation, parity, and time reversal symmetry, then the violation of time reversal symmetry implies the violation of CP symmetry. And then we can use this fact to study physics beyond the standard model using this kind of interactions involving molecules or atoms. So how do we do so? Basically, we start writing a Hamiltonian like this, where we treat the eEDM Hamiltonian as a perturbation using perturbation theory. We can write the first order correction to the energy in this way, where these wave functions are the solution, the stationary states that are solution of H0 of the molecular Hamiltonian. And then these are parity even or parity odd wave functions. And as I said, the eEDM Hamiltonian is a parity odd operator, which means that this is exactly 0. Then we need to, if we want to see the effect of this eEDM in a molecule, we need to turn on an external field, an external electric field, in such a way that we can mix, two states with different parities. And this is valid both for atoms and for molecules. Why is it then convenient to use molecules? Because in molecules, we know that we don't only have electronic states, but also we have the vibrational or rotational states. So we can use close-lying rotational state with opposite parities. And as this difference in energy is in the denominator of this expression, we have a large enhancement of these effects in molecules. And why do we study in particular ytterbium-containing molecules? First, because it was a suggestion of one of our colleagues, Professor Thomse, and because these molecules have a couple of favorable conditions. Between them, we can mention this small energy difference between the rotational states that I mentioned before. Also because these are heavy element containing molecules, and then the relativistic effects are quite important here. And finally, because these metals, in principle, theoretically, could be laser cooled, and then they can be associated to form a molecule, and then we can improve our precision of the measurements. So the effective parity and time reversal violating spin rotational Hamiltonian that we use, experimentally speaking, it looks like this, where WD and WS are what we call the enhancement molecular factors. They cannot be measured, they need to be calculated. This will be the energy shift due to these interactions. And as I said, these two molecular parameters need to be predicted theoretically, so we need to calculate them to interpret the experimental results using relativistic methods, using a relativistic context. To calculate in first place WD, one of these enhancement factors, we start from the salpeter Hamiltonian, and then here in this expression, the electric field comes from three different sources. We have the electric field at position of the electrons coming from the, or produced by the nuclei in the system, by the electrons in the system, and from external sources. Here in particular, we have two electron interactions, and these are hard to treat using electron structure methods. So it has been proposed many years ago, or a couple of decades ago, that under certain circumstances, the mean value over the electronic wave functions of this Hamiltonian is equal to the mean value of two other effective Hamiltonians that we call effective Hamiltonian 1 and 2, or two different stratagems. The second one is most widely used in the community because it's just the sum of one electron operators. And the second one here has still the electric field, but it has been shown that the main contribution in this case comes only from the electric field produced by the nuclei. So by using perturbation theory and then applying the finite field method, we can calculate the first order correction to the energy, and then we can get this enhancement parameter. And we can do something similar with the enhancement factor, which is called WS. This arises from the scalar, pseudoscalar electron-nucleon interaction. This is also a CP violating interaction that involves the electrons in the systems, so this is why we need to calculate it. Here GF is the Fermi coupling constant, gamma 0 and gamma 5 are the Dirac matrices, and rho is the normalized density of the nuclei in the system. Again, here we use perturbation theory, we apply the finite field method, and we can calculate WS. Regarding the computational approaches that we use, in particular, we use a four-component Dirac Coulomb Hamiltonian. We use to account for the electron correlation effects. We use the Fock space coupled cluster method, and we expand our atomic orbitals in terms of Gaussian basis sets. And so we combine all these features by using the Dirac code, so we can get accurate relativistic results, and we can also estimate the error bars of our predictions. So in first place, let me here show you some values of WD using the two approaches. This is the most usually used, let's say. This one we needed to implement. This one hasn't been studied in molecules using four-component approaches. So here I show you ytterbium copper, ytterbium silver, and with gold. And in particular, it's useful to see what happens with this approach when we analyze these molecules, because you can see that the values are very small for this molecule, and this can be explained by using this stratagem, because then we can calculate the electric field produced by both elements in the systems, and then if we sum both columns, let's say, we get this dashed line, and there is a very good agreement between the two results. Then we study another kind of effects, for example, the influence of the nuclear charge density distributions and the two different factors. Then we also analyze the influence of the basis sets and the influence of the electron correlation using Hartree-Fock, MP2, Fock space coupled cluster with single doubles and triple excitations, also analyzing different active spaces and so on. And then finally we were able to compare our results with results in similar molecules, in other molecules that has been analyzed recently. And then we have seen that the results for ytterbium copper and for ytterbium silver in particular, they are quite interesting. And to get the analysis of the sources of uncertainty, or to get reliable error bars, we analyzed the influence of using different basis sets, including more or less diffuse and tight functions to describe different regions of the electronic density. Also, we, as I said, use different electronic correlation methods, and also we include the analysis of the vibrational corrections. With all this, let me then conclude that we have seen that ultra-cold molecular assemblies of ytterbium copper particularly, and the molecules also containing silver, are promising candidates for future experimental searches for the eEDM, for the electronic electric dipole moment. The molecular enhancement factors or parameters decrease with the atomic number of the ligand metal, and we have seen that using these electronic structure methods, we can calculate these enhancement factors in the 3 molecules, including reliable error bars. And let me finish by acknowledge our collaborators in the University of Groningen and here, and thank you very much for your attention.
Thank you, Ignacio. We are open now for questions.
Okay, so I steal your microphone. So a question about these molecules. So right, one of the parameters that makes a molecule a good candidate is this effective electric field and sensitivity. But another important parameter, for example, for hafnium fluoride plus and for thorium oxide, is the fact that they have these triplet delta 1 states, or an equivalent state, where they have very, very low magnetic G factors in them, and it also allows you, this lambda doubling parameter allows you to polarize the molecule. So the question is there an equivalent in this molecule?
Here, another argument, I mean, there are, I think, a couple of factors. Another factor that is not mentioned is this molecule have a very large dipole moment, what chemists call permanent dipole moment. But yeah, I mean, I've only mentioned some of them.
I see, okay.
Yeah.
Okay. But they exist, these kinds of states exist in these molecules?
Yeah.
Okay.
Yeah.
Thank you.
Thank you for a very nice talk. I assume that during your electronic structure calculation you use the Dirac-Coulomb Hamiltonian, and my question is what with the higher contributions like Gantt or I don't know, even QED contribution?
Yeah.
How it's can influence your result?
Yeah. In principle, there are many things that we can, many other effects, higher effects if you want, that we can include. But for instance, just starting even from the beginning, even starting from this equation, here we are suppressing the magnetic interactions. So, and those haven't been calculated before for molecules, they have been calculated for atoms, and it has been shown that these are very small. So, in principle, we cannot say that even those contributions are smaller, for example, than the bright contributions or QED. So, in principle, and some of the works, for example, these works by Sanders, Martenson, and Lindroth, they also showed that you can only do this kind of approaches, so you can use this approach only if you suppress bright interaction, for example, only if you suppress the magnetic interactions here. So in principle, they are expected to be much smaller than these main contributions. Of course, if you want very, very accurate results, you should include them, but in principle, we are given like, I would say not only order of magnitude, but they should be below the error bars that we have seen here. They should be very small.
I have a curiosity. I am not expert in relativistic effects. I agree with you that electron correlation and relativistic effect are crucial here. I also realize that in the first case, in the correlation energy, you are using couple clusters, singles, doubles, and triples, so probably that is more than accurate. But my question is how, and you mentioned accurate relativistic effects, and so my question is how much accurate with respect to electron correlation, because there are two components which are independent. So you can have very well treated electron correlation effect and very well treated relativistic effect, but still the errors in both things being quite different. That is just a curiosity.
Yeah. I have not a good answer, I think, for this particular property, but it has been shown in many of the molecular properties that I know, that there is, of course, you can analyze correlation in one hand, let's say, using this very simple and basic plot, let's say. No, it was not here. Or yeah, it was before. No, sorry. It was here. Yeah, this one. They are not completely independent. I mean, you cannot decouple the relativistic effects from the correlation effects in principle, of course. But in this particular case, as we are treating relativity from the beginning, let's say, using this 4-component code, we are not using SORA or other kind of approaches. We are starting from 4-component approaches. Then in principle, we can say that everything is mixed up inside. In this way, we don't need to decouple both kind of effects.
So we have one question more.
Yeah, thank you very much. So YBF, of course, has also been looked at in detail, and when people try to laser cool that, there's found that there's a real problem with the 4F whole states, right, in these molecules. I was wondering, in these species, do they also have these 4F whole states that might be at problematic energies, or is this in a different range, or is that known? Is that looked at?
I really don't know. Maybe Michal, you know something about this? I really don't know.
So the question is it a problem for you? Here?
Yeah.
Because you don't need to laser cool. So
Yeah, sure. I mean, so if you don't need to laser cool, then it's not a problem. But most of these experiments, if you want to do them to the ultimate limit, you would like to laser cool, right? I mean, so that was, and I was just wondering where these were energetically in these species, because they might be higher up.
no, I think they may be accessible, but the point is that here the idea would be to assemble ultra cold molecules from atoms and then just measure,
Yeah. Okay.
not without any laser cooling. I think
Okay.
that here there is no scheme for laser cooling.
Okay.
I can also wait for the break. But so one of the questions is regarding the fact that some of these molecules have a nuclear spin. And so this nuclear spin, it actually follows this CP violating force. And if you have some nucleon interaction, BSM forces, so actually, right, you had 2 parameters on there. So for some of these, you need to add a third BSM interaction.
Yeah, we didn't
Perhaps.
calculate it. In principle, we are assuming that we can get some isotope without a nuclear spin. But it's completely true. I mean, if you include a non-zero spin, you also need to include this nuclear quadrupole moment dependent contribution. I mean, there is a third enhancement factor. And in some cases, it's quite large.
So for some of these examples, there was no isotope. There is no other isotope. But it's interesting to...
Okay, good point.
Yeah.
Good point.
But no, it's interesting.
Thank you.
Really interesting.
Yeah.
So now we are on time, almost on time, for the lunch. So we conclude this session. Thanks again to the speaker, and thanks to everyone.